We will discuss the concept of work done by a force. Well, first of all, you know what a force is. Now, a force is primarily responsible for doing work. And therefore, let's first of all talk about a force and how force is measured. Now, you know the concept of acceleration. Acceleration is the change of velocity. The change of velocity for a moving object can be caused only by a force. And according to Newton's law of motion, the net force acting on an object is represented by F equal to ma, where m is the mass and a is the acceleration. If I'm able to apply a net force F on this car, it produces an acceleration A on the car, such that F equal to ma. Now, m is measured in kilogram, and acceleration is measured in meter per second squared. Now, this unit, kilogram meter per second squared, is called a Newton. So the unit for measuring force is a Newton, and we represent it by the uppercase N. Now, tell me, if I have this mass, this is actually 1 kilogram. Now, there is a force acting on it due to the pull of gravity of the earth. And that force is called the weight of this object. What is the weight of this m kilogram? Well, its mass is m. What is its weight? Remember, weight is a force. Force exerted by the earth, the pull of gravity. That means if I leave this object, I don't want to drop this one, but here, if I drop this, it's going to go down with an acceleration. What is the acceleration of free fall? The acceleration of free fall is represented as g, and its normal value is 9.8 meter per second squared. That means the pull of gravity can produce an acceleration of 9.8 meter per second squared on any falling object. And therefore, what is the weight of an object? The weight of an object is mass multiplied by acceleration due to gravity. So, if this object has a mass of, let's say, 0.5 kilogram, and the acceleration of free fall is 9.8 meter per second squared, and therefore the weight of this object is 0.5 kilogram times 9.8 meter squared, meter per second squared, which is 4.9 kilogram meter per second squared, is the Newton. Well, so you now know that the force is measured in a unit called Newton, and the weight of an object is a force. The weight of an object is measured in newtons. Now, here I have a scale that measures the weight of an object in Newton. Now, I want you to look at the weight of this object in Newton. I'm going to hold it near the camera. Now, watch when it comes clear, if it comes anytime clear at all. Now, let's see. All right. Now, it's coming clear. It is marked in Newton. You can see it up there. Is that right? Marked in Newton. And the weight of this is about 9.8 Newton. This is 1 kilogram. The weight of 1 kilogram is 9.8 Newton. Now, for all practical purposes, we're going to use that 9.8 as 10 because it is much easier to deal with the number 10 than 9.8. And so, if I ask you what is the weight of a 10 kilogram object, what is the weight of a 10 kilogram object? We would say 10 times 10, 100 Newton. And one more thing. Tell me, if I have an object resting on a surface like this. Now here I have an object resting on a surface. What is the force that I need to apply to just lift it? I'm just lifting it. The amount of force I need to apply is a measure of its weight. So in order to lift an object, you need to apply a force equal to its weight. Alright, now having given this introduction, let's talk about work done by a force. Well, when does a force do work? A force does work only when it produces motion or when it produces a displacement. Now, so work done by a force is actually measured as the product of the displacement it produces and the force. So work is a measure of the product of force and displacement that the force produces. For example, if I apply a force of 10 Newton and moves an object by 2 meters, then the work done is 10 Newton times 2 meters. And that's how we measure work. So force is measured in a unit called Newton. I told you that. So a force F Newton applied on a box. Now look at the box sitting here, and I apply a force F Newton on it and produce a displacement of X meter on it. So a force F applied on this box displaces the box through a distance of X meter. Therefore, work done is force measured in Newton multiplied by displacement measured in meter. So it is force multiplied by displacement. And what is the unit of that work? Newton times meter. And the Newton times meter is called a joule. So work is measured in a unit called joule. We represent it by the uppercase J. Work done is measured in joules. Now, if I want to lift an object, say, upward by applying a force F, and I lift it through a height h. So if the box on the right shown here is lifted through a height h equal to 3 meters using a force of 200 Newton, what is the measure of the work done? Can you tell me what is the work I need to do to lift that box? Suppose this is the box that I need to lift. I apply a force of 200 Newton on the box and lifted it through 3 meters. What is the work done? Well, of course, the work done is the force applied multiplied by the displacement it produces, and therefore it will be 200 Newton times 3 meters. That will be 600 joules. That will be the amount of work that is done in this case. Now, this definition of work done and this method of measuring work done is useful only if the force remains a constant throughout the displacement. Now, for example, when I want to lift this mass, now I'm lifting it through a height h, and I calculate the work done as the force I applied multiplied by the displacement. Now, this is useful only if the force remains a constant throughout the displacement. Now, in all such cases, it may not be true. If the force remains a constant throughout the displacement, then we don't need to discuss this in a calculus class. Obviously, it means that we are going to look at cases where the force changes with displacement. Now, how do we deal with work done in such a case? So, the simple definition of work equal to force multiplied by displacement will work only if the force remains a constant throughout the displacement. If the force changes with displacement, then we used to use the method of calculus to measure the work done. Now, how does the method of calculus going to help in measuring work done in such a case? Now, here I have an object. I want to lift it all the way over here. Well, maybe to the space station. Now, actually, the weight of this object is going to be different as we go away from the Earth. That means the force acting on this, or the force required to move it, will change from point to point. And therefore, work done equal to force times displacement will not work here. Why? Because this force will keep on changing. So, what's the method, or how does the calculus method help there? Well, what we do is, we will take a very small displacement we call dr, and we would say, in this very small displacement, in the interval of that very small displacement, the force is going to remain a constant. Is that right? Although the force changes with the height, we can imagine that for a very small interval dr of displacement, the force will remain a constant. And therefore, we can calculate the small work done dw to move that object through a small displacement dr is f times dr. And then you can actually take the dr anywhere in here and add all these dw's from, say, h equal to c to h equal to d, and integrate from h equal to c to h equal to d of this dw. That will give you the complete work done. And that is the method of calculus that we're going to use. Now, one example where the force will change with displacement is in the case of stretching a spring. I'm sure you are familiar with this. If I want to stretch a spring, I apply a force on it. Now here I have a stretching force. Now if I want to stretch the spring further, I need to increase the force. Look at this. I need to increase the force. If I want to produce further displacement, I need to increase the force. This means the displacement is actually proportional to the force. Or I will say the force, the stretching force, is directly proportional to the amount of stretch or the amount of displacement. Or in this case, we will say F equal to kx. The stretching force keep on increasing as the displacement increases. If I want to produce a further displacement, I got to increase the force. Therefore, we say the stretching force increases as the amount of stretch increases. Now remember, amount of stretch is the displacement. So as the displacement increases, you need to increase the force, or F equal to kx. For a spring, this law is called Hooke's law. Very important law, which says the amount of the force needed to stretch a spring is proportional to the amount of stretch. You increase the force, the stretch will increase. Now we're going to use all this and use the method of calculus to obtain the work done in various cases. Now look at this graph of force against displacement. You can see the force does not remain a constant throughout the displacement. So how do we measure the work done? What we do is we take a very small strip of displacement dx. So consider a very small displacement dx where the force remains a constant. We will assume that during this displacement dx, the force will remain a constant. And so, what is the small work done during that small displacement? dw equal to force multiplied by that dx. Now, if the displacement now takes place from x equal to x1 to x equal to x2, what all we need to do is integrate this dw from x equal to x1 to x equal to x2 to get the total work done. So we say w equal to integral x1 to x2 of f dx. And we will be able to calculate the total work done that way. Alright. First of all, we will consider work done in stretching or compressing a spring. I just showed you that in order to stretch or compress a spring, the force will depend on the amount of stretch. Alright. Now, here I have a spring. The figure shows a spring fixed to a support. If I apply a force, a compressing, now what I showed you here is a stretching force. Is that right? In the same way, you can also compress a spring. Now, here a force F is applied to compress the spring. Now, you can see the force has actually compressed the spring a distance dx. So from this initial length of the spring, it has been now compressed by a small displacement dx. Now, in order to compress the spring further, if you want to compress the spring further, your force needs to be bigger. As you compress the spring more and more, you need to apply more and more force. So, a greater displacement x requires a greater force. That means the force keep on increasing with the displacement, and we say the force F is proportional to the displacement. I just showed it to you earlier, and I can write it as F equal to kx. Now this k, what is this k? This k equal to F over x. It is the force needed to produce a unit displacement, and that is called the spring constant. That's right. K is called the spring constant. What is the unit for measuring that spring constant? Force is measured in Newton. Displacement is measured in meter. Therefore, K, the spring constant, is measured in Newton per meter. How many newtons of force is required to stretch that spring by 1 meter? That is the value of K. In fact, many springs have different K value. Is that right? Small K value to a very high K value. The spring for the suspension of a car has a great K value, whereas the spring that you use for your pen has a small K value. Alright, now if the spring is compressed from an initial position x equal to x1 to a final position x equal to x2, then the total work done, so the spring is compressed from here to here. And remember, in order to compress the spring to a very small displacement dx, the work done will be f dx. and therefore the total work done when the spring is compressed from an initial position x1 to a final position x2 is W equal to integral x1 to x2 of f dx, and in the case of the spring this f equal to kx, and this k is a constant, we can bring it out of the integral sign, so that will be k times integral x1 to x2 of x dx. What is integral of x dx? It will be x squared over 2. That will be k times x squared over 2, x changing from x1 to x2. Now if you apply the upper limit minus the lower limit, you get the total work done is k over 2, bring that 2 outside, k over 2 x2 squared minus x1 squared. This is the measure of the work done when a spring is stretched from an initial position x1 to a final position x2. Alright, let's do a problem. A particular spring has a force constant of 2.5 times 10 to the power of 3 Newton per meter. This is the K value. How much work is done in stretching the relaxed spring 6 centimeter? Well, you need to stretch it to 6 centimeter. That means you can call the initial position 0 and the final position 6 centimeter, can't you? Yes. Now, how much work is done in stretching the spring an additional 2 centimeter? Well, the force involved in stretching the spring is identical to the force required to compress it. So, the law F equal to kx is valid for stretching the spring or compressing the spring. And therefore, the equation we developed as W, the work done, equal to k over 2 times x2 squared minus x1 squared is equally applicable for stretching the spring or compressing the spring. That's right. So you got k equal to 2,500 Newton per meter. The spring is stretched from a position x1 equal to 0 to x2 equal to 6 centimeter, which is 0.06 meter. So this is x1 equal to 0. We measure it from here. And this is x2 equal to 0.06. That means this amount of stretch is 6 centimeter, which is 0.06 meter. So what is the total work done? Work done is integral x1 to x2 of f dx, and we can replace f by kx, where k equal to 2,500 Newton per meter. So I replaced f by kx, where k is 2,500. And x1 is 0, x2 is 0.06. And 2,500 is a constant that comes out. And integral 0 to 0.06 x dx. And integrate x dx, we will get x squared over 2. That will be 2,500 x squared over 2 from 0 to 0.06. Well, apply the upper limit. We can ignore the lower limit because the lower limit is 0. And that will be 2,500 times 0.06 squared over 2. And that is 4.5 joules. In order to stretch the spring from its relaxed length to through a distance of 0.06 meter is 4.5 joules. Well, our B part, how much work is done in stretching the spring an additional 2 centimeter. So now you have stretched the spring 0.06 meter. You need to stretch it by an additional 2 centimeter. Means if your x2 is 0.06 meter, your x3 is 0.08 meter. So the spring is stretched from its position x2 equal to 0.06 meter to x3 equal to 0.08 meter. Therefore, we can still use the same equation, but your x2 is 0.06, x3 is 0.08, your k value is the same, is that right? So that will be w equal to 2500 integral 0.06 to 0.08 x dx. That will be 2500 x squared over 2. Lower limit is 0.06, the upper limit is 0.08. Alright, we apply the upper limit, replace x by 0.08, minus, replace x by 0.06, and that will be inside this bracket. So that is 2500 over 2, we take that to outside, multiplied by 0.08 squared minus 0.06 squared. Remember this 2 has come out. And what's that equal to? That is 3.5 joules. So, in order to stretch the spring end initially by an amount of 6 centimeter, we used how much work? 4.5 joules. To stretch it an additional 2 centimeter, we've done 3.5 joules. If you want to stretch another 2 centimeter, tell me, will the work done be this, greater than this, or less than this? It will be greater than this, because as you keep stretching, you need to apply a greater force. Alright, another one. A 200 Newton force stretches a spring by 10 centimeter. What is the work done in stretching the spring by 15 centimeter? Well, in this case, we are not given the value of K, the spring constant. Is there sufficient information in the problem that let you do that? Yes, look at this. A 200 Newton force stretches the spring by 10 centimeter. F equal to Kx. Is that right? Now our F is 200 Newton, X is 10 centimeter, 0.1 meter. And you know that the stretching force on a spring is F equal to Kx. When F equal to 200 Newton, X equal to 0.1 meter, therefore we can find that K. K equal to F over X, that is 200 Newton over 0.1 meter, that is 2000 Newton per meter. I hope you understand the way I write this. Newton per meter, Newton divided by meter is the same as Newton meter to the negative 1. This is the standard way to write the unit, and not Newton per meter with a slash. It must be Newton meter to the negative 1. Alright, now that you know the value of K, we need to find the spring is stretched from a position x1 equal to 0 to x2 equal to 0.15 meter. So, this is x1 equal to 0, and the force F stretches the spring to x2 equal to 0.15 meter. The work done is integral x1 to x2 of f dx. And what is F equal to? F equal to Kx, where K is 2000. That's right, where K equal to 2000 Newton per meter. So, the work done will be integral 0 to 0.15, x1 to x2, 2000 x dx. That will be 2000 comes out, 2000 times integral 0 to 0.15 x dx, and x dx integrated gives you x squared over 2. Lower limit is 0, the upper limit is 0.15. Here again, the lower limit does not give you a value, so you don't need to worry about it. So, simply replace x by the upper limit. That gives you 2000 times 0.15 squared over 2. That is 22.5 joules is the amount of work that is done in this case. All right. So far, we were looking at the force that is required to stretch a spring, and we know in the case of a spring that force varies with the displacement. How about work done in propulsion? When you want to propel something from the surface of the earth into space. Now remember, in order to lift an object, the amount of force you need to apply is its weight. But if you take an object away from the surface of the earth, its weight is going to decrease. That means the force that you need to lift an object decreases as the altitude increases. And so, if you want to find the work done in propulsion, you must have an idea how the force decreases with distance. The force needed to lift an object depends on the altitude of the object. And according to Newton's law of gravitation, now Newton's law of gravitation says the force decreases inversely as the square of the distance. If r is the distance of an object from the center of the earth, then the force F needed to lift that object is given by F as a function of r equal to k over r squared, where r is the distance measured from the center of the earth. So, as you move away from the center of the earth, the force needed to lift an object is reduced, made smaller and smaller according to this relation, where k is a constant. All right. Now, here k is a constant that can be determined from known information. For example, if you know a given altitude, and if you know the force that is needed to lift the object at that altitude, we can then find the value of k. We will do that as we go on in solving problems. Now, if an object is lifted from a distance r1 from the center of the earth to a distance r2 from the center of the earth, the work done is given by W equal to integral r1 to r2 of f dr. Now, let me take a minute to explain that a little more clearly. Let's imagine that this is the earth. This is the center of the earth. Now, we need to move an object, say, from the surface of the earth to somewhere here. Now, this is your r1. r1 is the initial distance of the initial position from the center of the earth, and this distance is r2. So we need to lift the object from a distance r1 to a distance r2, and you cannot use work done equal to force multiplied by displacement, because the force will keep on changing. Now, what is the nature of that force? We said that force equal to k over r squared. Now, what's the method we do? We take a small displacement dr here. We will assume that the displacement, during that displacement, this force will remain a constant. And therefore, the small work dw will be force times that small displacement. And force equal to k over r squared. So force multiplied by that small displacement is this. And all we need to do to calculate the total work done to move the object from the surface of the earth to the space station is the total work done will be integral r1 to r2 of this dw k over r squared dr. Now that's the method we are going to use in solving problems in this section. So the total work done to propel an object from a distance r1 to a distance r2 is given by integral r1 to r2 k over r squared dr, and that will be k times integral 1 over r squared dr. Alright, how many of you can tell me what is integral 1 over r squared dr? Integral 1 over r squared dr. Now remember, the derivative of 1 over x with respect to x is negative 1 over x squared. Therefore, integral of 1 over x squared dx is negative 1 over x. Integral 1 over r squared dr is negative 1 over r. You can also do it using the power rule. 1 over r squared is r to the power of negative 2. Integral of r to the power of negative 2 dr is r to the power of negative 2 plus 1 over negative 2 plus 1. And that will be negative r to the power of negative 1, which is negative 1 over r. Now try that writing down on your own. So if an object is lifted from the surface of the earth, you see, if object is lifted from the surface of the earth, then this r1 will be the radius of the earth. And we will use the radius of the earth as 6.4 times 10 to the 6 meter. In other words, it is 6.4 million meter is the radius of the earth. Wherever we need that, we will use this value. Alright. Also, I told you earlier in this lesson that if an object has a mass m, the gravitational force on it by the earth is its weight. Force of gravity on an object of mass m is m times g, where g is the acceleration produced by the force of gravity, and its value is 9.8 meter per second squared. All this we talked about earlier. So, if a satellite has a mass of 2 metric tons, then the minimum force required to lift it is its weight. The minimum force that you require to lift a satellite of mass m equal to mg. So that m is 2 metric ton. A metric ton is 1,000 kilogram. So the 2 metric ton is 2,000 kilogram, and the g equal to 9.8 meter per second squared. Therefore, the total force necessary to lift this satellite off the ground is its mass times acceleration due to gravity. That is 19,600 Newton. You need a minimum force of 19,600 just to lift this satellite from the surface of the earth. That's right. This is the weight of the object. And to lift it upward, you need to apply an equal force upward. That's right. Okay, let's do a problem. Neglecting air resistance, determine the work done in propelling a 4 metric ton satellite to a height of 200 kilometers above the earth. And B, calculate the work done to propel it 400 kilometers above the earth. Well, if you can do this, then you can do that. The only thing is, replace your R2 by 200 kilometers here, and this is 400 kilometers above the earth. Alright, the force needed to lift a 4 metric ton satellite. Now, what is the force that you need to lift that satellite from the surface of the earth? Is equal to its weight, its mass times g, which is, mass is 4 metric tons, 4,000 kilograms. G is 9.8, so that will be 39,200 Newton. That is the minimum force you require to lift it off the ground. So, its weight is 39,200 Newton, means when the satellite is on the surface of the earth, its distance from the center of the Earth. What is the distance of the satellite from the center of the Earth when it is on the surface of the Earth? It is the radius of the Earth. And the radius of the Earth is 6.4 times 10 to the 6. This is your R1. Now, what is your R2? R2 is 200 kilometers above the surface of the Earth. That means R2 will be this radius of the Earth plus this 200 kilometer. That's right. Now, using Newton's law, the force needed to lift this satellite, is actually an upward force equal to 39,200 Newton. And according to Newton's law, this force must be equal to K over R squared. And on the surface of the Earth, it is K over RE squared. That is, you see, the weight of the object on the surface of the Earth is this 39,200. Remember, this 39,200 is the weight of the satellite only on the surface of the Earth. As it is lifted away, its weight will be something less than that. So, when the distance equal to the radius of the Earth, the weight of the satellite is 39,200. We can use now these two values to find K. One more time, in this equation, F equal to K over R squared, when this R equal to the radius of the Earth, the force needed to lift that off the surface of the Earth is 39,200, the weight of it on the surface of the Earth. Therefore, what is K equal to? K equal to 39,200 multiplied by this number. That's a big number, 1.606 times 10 to the power of 18, and that is the value of K. Alright, we will now use this value of K to find the work done when the satellite is lifted from R equal to R1 to R equal to R2. Well, so we have these values. We know K. We know that the force that is needed to lift the satellite is of the form F equal to K over R squared. That means this force will change with this R. Well, using the value of K, we have F equal to 1.606 times 10 to the 18 divided by R squared. And we know this. The total work done to lift the satellite from a distance R1 to a distance R2 from the center of the Earth is integral R1 to R2 of FR dr. And we can now replace this F of R with this expression. That will be integral R1 to R2, 1.606 times 10 to the power of 18 divided by R squared dr. This is a constant, we can take it out. So the constant number comes out, and you have integral R1 to R2 of 1 over R squared dr. Alright, what is R1? R1 is the distance of the surface of the Earth from its center, which is the radius of the Earth. And what is the radius of the Earth that we said we will be using? It will be 6.4 times 10 to the 6th meter. And what is R2? R2 is 200 kilometers above the Earth. That means the total distance is the radius of the Earth plus 200 kilometers. That's right. So R1 is the radius of the Earth, and R2 is the radius of the Earth plus 200 kilometers. But of course you need to convert that 200 kilometer to meter. 200 kilometer is 2 times 10 to the power of 5 meter. Now add these two, you get 6.6 times 10 to the power of 6 meter is R2. So we can now replace R1 and R2, and we can perform this integration. Therefore the work done is 1.606 times 10 to the power of 18 integral 6.4 times 10 to the 6 to 6.6 times 10 to the 6, 1 over r squared dr. Alright, tell me, what is integral 1 over r dr we just talked about a while ago? Integral 1 over r squared dr is negative 1 over r. Why? Because the derivative of 1 over r with respect to r is negative 1 over r squared. And therefore, integral of negative 1 over r squared is 1 over r. Integral of 1 over r squared dr is negative 1 over r. That's right. So, it will be that constant, which we know what it is. Integral 1 over r squared dr is negative 1 over r. This is the lower limit, and that's the upper limit. So, what all we now need to do is replace r by the upper limit minus replace r by the lower limit, and then multiply that quantity with this constant. Alright, let's do that. That will be 1.606 times 10 to the 18 times negative 1 over upper limit is 6.6 times 10 to the negative 6 minus the upper limit minus now the lower limit. Again we have that negative 1 over r1 is 6.4 times 10 to the 6. Now simplify that. First of all, these two negatives become positive. Is that right? That become positive. So I'm going to write this quantity first. Look at that. Negative, negative, positive. So 1 over 6.4 times 10 to the 6 is the positive quantity I write first. Minus 1 over 6.6 times 10 to the 6. And this can be done on your calculator without any trouble. And the result is 7.6 times 10 to the 9 joules. That is the amount of work needed to propel that satellite from the surface of the Earth to an altitude of 200 kilometers. Alright, now this is the original question. We did this. I want you to do now this. Do that on your own. So do part B on your own and make sure that you can solve any such problem of propulsion using the method we developed here.